So about the contents, yeah. Here we have the table of contents, and I have to say that this lecture includes all the chapters except number 2 to 5, which is the logic part. So there will be no logic in this lecture. I mean, there is a simple reason why we have no logic here, because the logic is included in the lecture Theoretical Computer Science, which will be given next semester. This is an compulsory course for the Master Computer Science, but not for the other masters. But of course it is optional for the other masters. So this is one reason. Second reason is that this whole contents would be too much for a 4-hour lecture. So we split it up and put the logic into the Theoretical Computer Science, and here there will be no logic. But I mean, you don't actually need the logic for all the other chapters, number 1 and 6 through 10. So there will be no problem without deeper knowledge of logic. Of course, you need to know a little bit of propositional logic, but that's all you need to know. And it turns out that in modern AI, I would say between 80 and 90% of all applications of AI are without first-order logic. I mean, first-order logic is getting a little bit more interesting again in the areas of semantic web and in robotics too. I mean, high-level planning for robots involves deep knowledge of first-order logic, but most of the other fields in AI, they don't need any predicate logic. So you will actually learn about the modern areas of AI without knowing the logic. And if you're really interested in logic, come to the Theoretical Computer Science lecture next semester. It will be about 1/3 of the semester. Actually, the first third of the semester will be the logic part. Okay, so we will now start with the introduction and then continue with searching, then reasoning with uncertainty, which is very important nowadays in AI, because in everyday reasoning you almost never have full knowledge of the state of the world, and also your knowledge is not certain. Then very important is machine learning and data mining. Actually, machine learning is the core of AI. Many people say that a system is not intelligent unless it is able to learn. Then neural networks, I made a separate chapter because it is a big area, but it, of course, is part of machine learning. And also reinforcement learning is part of machine learning, but it's its own area in AI nowadays, and therefore we have these separate chapters 9 and 10. Okay, so let's start. Oh yeah, I mean, this is the bibliography. We don't go into detail now. But let me say one thing about books. And this is pretty short. Apart from this book, there is the AI Bible. This is the book from Russell and Norvig, Artificial Intelligence. But I mean, if you look at this book, which is a thickness of about 1 centimeter, then the Russell-Norvig book is like that, more or less 10 centimeters. I mean, this book has around 300 pages. Russell-Norvig I don't know, something between 1,200 and 1,500 pages. So it's between 4 or 5 times as much volume as this book. And that's actually the reason why I wrote this book, because students complained. I mean, no student is able to read 1,500 pages. I mean, you could read it, but the question is, can a student understand these 1,500 pages, apart from taking very much time? And so I finally decided to write this AI book. First I wrote the German book, and then the German book turned out to sell very well, and so Springer, I mean, they look around which books sell very well, and then they asked me whether I would be interested in translating the book. And so you have the English book now. Okay, what is artificial intelligence? So what is intelligence, is the first question. If we want to talk about AI, of course we need to know what is intelligence. So we will talk about what is intelligence a little bit. How can intelligence be measured? This will also be covered a little bit. How does our brain work? This is a pretty interesting question. I mean, we could call AI as a subfield of this new area called bionics. I mean, in bionics, researchers try to copy nature. For example, airplanes are a not excellent copy of how birds fly, and artificial intelligence can be seen as trying to copy how our brain works. But there is a problem. The problem is that nobody knows how our brain works yet. Of course, there are these neurophysiologists, and they try to understand our brain, but I mean, I read books about neurophysiology. I also talked to Manfred Spitzer, who is a well-known person in neurophysiology, a professor from University Ulm. And I asked him, tell me how reinforcement learning in our brain works, which is very important. And then he said, oh, let me think. Oh, yes, I've heard there is a book, but I don't remember the title. And then I said, you mean the book of Sutton and Bartow called Reinforcement? Oh, yes, that's the book. And then I knew everything. Because this Sutton-Bartow book is a book written by 2 computer scientists who do not know what's going up in our brain. But they know about mathematics and AI, and they invented algorithms that make computers able to do reinforcement learning. So he was citing the book from my community, but he doesn't know how it works. I mean, they know a lot about our brain. They know about chemistry. There is dopamine and other neurotransmitters, and they know if, for example, you drink alcohol, then alcohol blocks these neurotransmitters and your brain doesn't work anymore. Okay, so they know how the brain does not work. But the interesting thing would be to know how the brain works if there is no alcohol or any other drugs. They know that there are roughly 10 billion nerve cells in the brain. They also know that every nerve cell is connected on average to something between 1,000 and 10,000 other nerve cells. So that means how many cables are there in our brain? So 10 billion times 10,000. So this makes 10 to the power 14, roughly, cables up there. And I mean, 10 to the power 14 is a pretty big number. So if the probability, I mean, in real machines or computers with so many cables, the probability that one cable, one contact fails, I don't remember, per hour or per day, is 1 over a million. So that would mean out of these 10 to the power 14 cables, 10 to the power 8, which is 100 million failures would be per hour or per day. But we don't have that many failures. Actually, we do have failures all the time, but our brain is fault tolerant, which is, of course, an excellent property. But that's about all we know about our brain. Of course, they know, okay, there is this area which is the visual cortex, and there is the olfactory cortex, which is about hearing, and then there is the memory and their language. They know these sections of the brain, but each one of these sections has billions of nerve cells, and they don't know the details. They don't know the wiring between the nerve cells. And if they can't give us the plan of the brain, how can we copy it? We can't. But of course it is fascinating. We all the time, we AI researchers, look at how we humans act, how we learn and so on, and try to copy it. But this is just from a behavioral view. We don't know about the details. Okay, so we are actually involved in building intelligent machines from scratch, more or less, and using, of course, mathematics. Then, of course, there is this science fiction matter. You know about these movies like iRobot and so on. Rebuild the human mind. We already talked about this. And there is a track going into philosophy. For example, I mean, when I show my robots to people, many of them ask, oh, this is interesting, this robot learns. Does this robot have consciousness? So it must have consciousness. So then there are these questions. Can a machine ever have a consciousness? Does this machine have a consciousness or not? Pretty interesting questions. Yeah. So now let's talk about what is intelligence. I will now give you a number of different definitions. So John McCarthy, in 1955, this was actually the birthday of AI. It was in 55 or 56 in, of course, the United States. And John McCarthy was one of the leading scientists who helped AI getting into this world. There was also Marvin Minsky and some other researchers. We will see their names on the next slides. And his definition of AI was, the aim of AI is to develop machines that behave as if they were intelligent. Yeah. But of course, what's the problem with this definition? There are many problems with this definition. But there is one obvious problem. I mean, unless we don't define intelligence, this doesn't help at all. So we need a definition of intelligence. Now, let me show you a movie. We can actually move a little bit forward. Okay. So you might consider this little robot intelligent. Huh? Maybe some of you would say it is intelligent, others would say it is not intelligent. At least it was able to solve the task. That means remove all the Coca-Cola cans from this area with the black stripe around it, and keep all the, what was the other, Pepsi cans in it. Huh? But now let me tell you how this robot works. This robot on the front has just a little touch sensor, and that's everything. Huh? And so what the robot does, and it has on the bottom a little sensor that tells him whether it moved across the black stripe on the ground. Huh? So the robot just randomly moves around, and when it crosses the black line, then it moves back again inside. And it does another random movement. And then there is this little touch sensor. Huh? If this sensor gives a signal to the robot, then the robot stops and goes back. Does another random movement, so it wouldn't push the can out if there is this signal. And so the only thing is, the Coca-Cola cans, they were full, the other way around. They were empty, and the Pepsi cans, they were full. So the touch sensor only gives the signal if there is enough pressure here. Huh? So it's extremely simple. It's extremely simple logic. Huh? So would you now still consider this robot intelligent? So the simple message is, not everything that looks as if it were intelligent is really intelligent. Huh? So we need maybe a somewhat deeper understanding of intelligence. Maybe that's what we need. But maybe we will not be able to define this term intelligent precisely enough. So the video we saw was actually pretty similar to what Professor Breitenberg, he used to be, I guess he is now retired. He used to be a professor in Tübingen at the Max Planck Institute, and he had this little experiment. He built very simple little robots like this or that, pretty similar to what we saw in the video. This is a robot with a light sensor here and a light sensor there, and this light sensor is directly connected to the motor for this left wheel and the right sensor for the right wheel. And that means the more light we have here, the faster this wheel turns, and the same with the other one. So that means if the robot is like this, and this is a light source, then there is a little bit more light on the left side, and the robot will make a right turn. So as a consequence, the robot will move away from the light. If you just switch these two sensors, then the behavior will be such that the robot moves towards the light. And I mean, still, this is extremely simple logic inside these robots. And now what Breitenberg did, he took a big room like that, empty, and then he put into the room a couple of these robots, maybe 20 of them. And for example, a light bulb in the middle of the room and nothing else. The rest is dark. So now what happens, if you take these guys, they'll all move away from the light, and finally they will crash into the walls of the room. So that they will be all around the walls of the room. These guys, they'll all move towards the light and hit into the light. Okay, this is not really interesting. But now the next step was, suppose we have all robots of this kind. And then he put on the back side, on the robot, a little lamp. Or maybe somewhere on top of the robot. He put a little lamp. And then we have these 20 robots in the room. Now what would then be the behavior? How would the room look like after a certain time?
Some of them can avoid from each other.
They what?
They can avoid from each other.
They avoid each other, yes, but how would the behavior in the room look like? And also you could imagine these guys with the light on them. How would the room look like here? I mean, actually what Breitenberg did was the other way around. He just put these robots in the room, let them move around, and then he had spectators, people watching these robots. And the people said, oh, look, this is intelligent behavior. That's what people said. Because what they saw with these guys is, this is like, it looked like the hall of a train station, with many people walking around or waiting for something. What happens? These robots, they will try to avoid each other. That means they will more or less distribute evenly around the room. And this looks like intelligent behavior. That's what people said. How about these guys? I mean, of course, there will be some crashes, robots really crashing into each other, which people interpreted as aggressive behavior. But also there will be some leaders and others following these leaders. Like in a queue, they just move around and I mean, as soon as one robot is behind this guy, it will always follow this robot. And of course it's even more interesting if you mix these and these guys in one room, and maybe you have some light sources in the room, or maybe around the border of the room everything is enlightened, so they won't crash into the border anymore. And so you can produce behavior that looks really sophisticated with these extremely simple agents. I mean, you know it from nature too. If you look at an ant colony, the behavior looks pretty intelligent, even though each individual ant is extremely simple. But there is this collective intelligence finally. Okay, another definition from the Encyclopedia Britannica. AI is the ability of a digital computer or computer-controlled robot to perform tasks commonly associated with intelligent beings. I mean, this is similar to McCarthy's definition, but a little bit more detailed. Commonly associated with intelligent beings. But according to this definition, every computer is an AI system, because doing sophisticated mathematical calculations is commonly associated with intelligent beings. Playing chess also. And actually, you know, computers play chess very well, I guess better than everybody in this room. Even the simplest PC chess software. So we might even conclude that these computers are more intelligent than we are. So this is not perfect either. And now I give you my favorite definition of AI. This is from Elaine Rich, an AI professor from the United States. And she says, artificial intelligence is the study of how to make computers do things at which at the moment people are better. I mean, this is kind of funny because it is not a fixed definition. It is a moving target. This definition changes from year to year. But this is actually what AI is all about. If we go 30 years back, around 1980, in journals about AI and on conferences, you could read and hear people writing and talking about chess computers, about new inventions in chess computers. This was really a topic in AI research. Today, there is no chess anymore in AI publications. Maybe 1 out of 10,000, something like that. One publication every year, or I don't know. But it vanished. And why? Because it's no longer interesting. We solved the problem. So it's no longer AI. It is, maybe it's computer science, whatever. But it's no more AI. What is the current fashion in AI? I mean, of course, one part is making the web more intelligent. Semantic web, this direction. But the main thread is autonomous agents, robots. Making robots intelligent. Because we do have the feeling that it is possible in the next 10 to 20 years to make robots really intelligent. But it is a real challenge. It's a real challenge. And the challenge is, of course, to solve these problems that we have not solved yet. So the challenge is not doing linear algebra on the computer. The challenge is these simple tasks like, if I ask you, please leave the room, then you have to get up, find the door, open the door and leave the room. This still is a real challenge for robots. For us it is trivial. Nobody would consider this as being intelligent, leaving a room. But for the robots, this is a real challenge. So this is the type of problems we work now in AI. And you see, this is perfectly covered by this definition. It is a pragmatic definition, and not all AI researchers like it. But this definition is what AI is all about. And this definition will still be up to date in the year 2050. I mean, this definition will actually always be true. Maybe this field of AI will end at some point. Maybe it will end at the point when robots are more intelligent than we are in every sense. Then maybe we won't do any research in AI anymore. Then maybe we will do research on how we can survive with all these robots around us. Yeah. Okay, brain research and problem solving. Yeah, we already talked about this. Yeah, let me show you this picture. This is the AI pharmacy. And this is more or less my view of AI. Oh, I don't know the English term. In Germany, I would say AI is a Gemischtwarenladen. So it's a supermarket where you can buy everything. But the question is, the trader in this store or in the pharmacy, if the customer comes and tells, okay, I have this disease, then of course the person behind the counter must be able to understand what kind of drug is good for this disease or for that disease. And since AI is a pragmatic science, an applied science, and we try to solve many different problems, starting from computer vision, ending in higher order logics, then of course this person behind the counter has to know about all the different diseases and about all the drugs for these diseases. So this means for AI, there is not this one technique from mathematics maybe, which you perfectly have to know and you can solve all the problems. No, it's different. I mean, there are many disciplines. For example, control theory. In classical control theory, you have to know the theory of differential equations and how to solve them and how to model a system, and everything is perfect and you can solve all classical control problems. Or in cryptography, you need to know number theory and then you are a good cryptologist. But here it is different. In AI, you have to know everything. That's the bad news, but it's like it is. You need fields like logic. And there are so many subfields in logic meanwhile, so logic is its own discipline. There is, of course, learning, machine learning. And there are so many different techniques in machine learning. There is this field of neural networks, search theory, reasoning with uncertainty, many different application areas, and so on. So this is, So if you have a good basic knowledge of computer science and mathematics, then you have good preconditions for studying AI. But I mean, it's very important that you know about many different of these areas. Classically, let's say 30 years ago, there was this logic fraction among the AI people, and this was very big at that time. Because at that time, until the 80s, the logic people believed that with logic we can solve all problems on this globe. That was the belief of the logic community, but it turned out they cannot solve all problems. It turned out that they can solve only very few problems. And we need other techniques coming from statistics, for example, which now is, I would say, the dominant mathematics used in AI. Strong statistics, which is not trivial at all. And I mean, a classical logician has no idea of statistics. So that's the problem. So the guys from this field and from that field, they haven't even been able to talk to each other. But things are changing now, and you need these different fields in order to understand AI. Okay, let's continue with the definition of AI. And the definition of how we can measure intelligence. And again, Alan Turing was a pioneer in AI long before AI existed. So this was around 1950 when Alan Turing invented, or let's say suggested, this Turing test. At that time, of course, there were no such computer terminals. But you know, Alan Turing, he developed the theory of computing long before there was the first computer. This was in the 1930s. Around 1944, the first programmable computer was developed. But Turing developed the theory long before. Also, he developed the so-called Turing test long before there was AI. And now, the idea is the following. So, there are these two walls here, which you have to imagine being bigger. So these persons can see over the wall. There are different rooms, okay? And there is this one person, this woman here, she sits on a computer terminal and she can communicate with some other agent on the other side. And she does not know whether on the other side there is another terminal with a human or there is a computer. You can see here this is IBM. So she doesn't know whether on the other side there is a human or a computer. But she has to find it out. And she can type in text in her terminal, and this text will appear on the screen of the human or in this computer. And then the other agent, of course, can answer. And depending on the answers, she has to decide, is this a human or is it a computer? Huh? So Turing defined passing the test such that if the computer can mislead Alice in 30% of the cases, then it already passes the test. And I don't remember, I think he even gave a time limit like 5 or 10 minutes. Huh? So if within 5 minutes, if there is the computer, with a probability of 30% it can fake Alice, then it passed the Turing test. Oh, that's quite interesting, and also it goes into the direction of the definition of Elaine Rich. So he doesn't talk about what's inside. He just talks about what happens. So is she able, from the text appearing here, to distinguish between computer and human? Yes, so, yeah. And so, much later, I don't remember when it was. I guess it was in the 70s. In the 1970s, Joseph Weizenbaum, who at that time was a computer scientist and AI researcher, he wrote a program called ELIZA, which actually simulated such an AI bot. And I don't remember, I don't actually know whether it passed the formal Turing test. But I know there are stories about Weizenbaum's secretary using this program, and she was, I guess she was a pretty lonesome person. Maybe she was bored in the office because she didn't have much work, and so she started talking to this ELIZA program. And there is the saying that Weizenbaum sometimes found her really for a long time talking to this program because she needed somebody to talk to. And nowadays there are these bots in the internet. So there is, for example, a bot called Cleverbot, Simon Levin, Alice Bot, and many others. And they, of course, are a little bit more intelligent than ELIZA was, and you can test them. It's quite a nice game testing them. And so if your questions are not sophisticated enough, the bot may cheat you. And you won't discover that it's a bot. But pretty soon you will see it's a bot. Okay, yeah. So let's talk a little bit about the history of AI. I gave you some figures about the history of AI already. I mean, there are people starting the history of AI in the old Egypt, or I don't know. But I think an interesting date is 1931, when Kurt Gödel, an Austrian logician, shows that in first-order predicate logic, all true statements are derivable. That means if there is a proposition which is true, then this first-order logic formal calculus is able to prove this is true. So all true statements can be proven. And this is, I mean, at that time, this was a real surprise for the whole community. It was a question that was stated in the year 1900 at the World Fair in Paris. There was David Hilbert, a famous mathematician. He made up the so-called Hilbert program, which consisted of around 20 questions. And one of the most fundamental questions was the question that Gödel answered in 1931. And he gave a positive answer. That's very important. So Gödel showed that mathematics is able to prove all true propositions, or to prove all the theorems in first-order logic. And the consequence was even more interesting for computer science, because he proved there is a formal system, and such a formal system can be programmed on every Turing machine. That means on every computer with every programming language, you can program a theorem prover that is able to prove all true theorems of first-order logic. This was really fundamental, and I mean, this really pushed computer science and, of course, AI forward. Look at this date. It was long before AI was invented, but, I mean, many logicians, at that time, this was the starting time when all logicians believed we can solve all problems on this planet with logic. We just need a powerful computer and a theorem-proving program. But Gödel proved that you can write this program. Okay, but a few years after this positive result came the negative result. And he proved that in higher order logics, this is no longer possible. He proved that as soon as your logic is just a little bit more powerful than first order logic, then it all crashes. That means there are theorems, true propositions, which cannot be proven. And that's very interesting for computer scientists, because in computer science we deal with languages all the time, with programming languages. And what Gödel proved is, as long as your language is simple enough, everything is fine. If your language is as simple as first-order logic, everything is perfect. You can prove all true theorems. But as soon as the language is a little bit more powerful, it all crashes. And the really bad news behind this second Gödel's theorem is that in AI we need higher order logic. With first order predicate logic, we cannot formulate all interesting things. I mean, look at what is first order logic. I mean, it's all about true and false. But we cannot talk about uncertainty. First order logic is not powerful enough to talk about incompleteness, uncertainty, and we will also see first order logic is a monotonic logic, and this is pretty bad for everyday reasoning. So nowadays we know that this second result really shows us the limits, at least of logic-based AI. But anyway, logicians, they were extremely optimistic until, I would say, the end of the 80s. Until about 1990, most logicians were extremely optimistic, and they believed that with logic we can solve all problems on this world. We just need a powerful computer, and that's it. But that was extremely naive, because already in the 1930s everybody knew that logic cannot solve all problems. And of course there came Alan Turing, who also proved the limits of computation. He proved the halting problem, which gives strong limitations for intelligence. This was in 1937. Then in 1943, McCulloch and Pitts, they gave the first mathematical model of neurons in the brain. So now you would say, oh, before you said we don't know the details of how our brain works. It's true, we know some details. I mean, this is like if you want to understand a microprocessor of such a computer. I mean, everybody knows how a transistor works. But does it help you understanding the microprocessor with billions of transistors if you know how one transistor works? No. Of course you need to know the plan, you need to know the wiring, and that's what we don't know. But we do know how one single neuron works. But that doesn't help us solving the problem. But anyway, in 1943 they modeled single neurons, and then a neural network is just a network of these neurons. So this was the start of neuroscience in computer science, but unfortunately at that time there were no computers. And therefore this development didn't really go forward until we had powerful computers. So we have to wait for some time. Then in 1950 there was the Turing test. 1951 Marvin Minsky developed a neural network machine with 3,000 vacuum tubes. He simulates 40 neurons. And I mean, if you have a computer with 3,000 vacuum tubes, this is not big fun, because these vacuum tubes, they are not really reliable. They fail pretty often. So if you have such a computer, maybe it runs for 1 hour and then a tube fails and you have to replace it and so on. And it's not very fast either, this computer. So and 40 neurons, this is not really much. But it was an important step forward. But still, this area of neural networks, it didn't really start. Then in 1955, Arthur Samuel, a researcher from IBM, he built a learning chess program. Why do we say? This is a typing error, I'm sorry. It was not a chess program, it was a checkers program. You know, checkers in German is Dame, Damespiel, which is much simpler than chess. But anyway, this was a real milestone in machine learning. This was the first computer program that learned to play a game. And at the end, it played better than its developer. And then in 1956, the term artificial intelligence was introduced. I already said this. Then, in the same year, Newell and Simon present the logic theories, which was the first computer program that deals with symbolic logic. So you could say the first extremely simple theorem-proving program. Then in 1958, McCarthy at the MIT invents the programming language Lisp. Lisp stands for List Programming Language, which still exists. This is a high-level language involving high-level data structures, lists. So you don't need to use pointers, you can work with lists. And you can work with symbols, and that's of course the precondition for implementing logic reasoning. So this was also a big milestone in AI. And he wrote programs that were capable of modifying themselves. Because it was not a compiled language, it was an interpreted language. So during runtime, the program is able to modify itself. So the program can add new statements to the source code. It can remove statements from the source code. It can modify the source code. And this, of course, is a fascinating idea. So this started the AI branch called genetic programming, genetic algorithms. Because genetic algorithms are like the DNA in a human body. The DNA is able to reproduce itself, and there is mutation. So the DNA changes, and then the agents that evolve from this DNA, they are different, they evolve, and so on. So this was the start of genetic programming. But to tell you the truth, genetic programming was not successful at all up to now. Because the complexity of this self-modification of a program, it's extremely high. And we humans do not understand how a program can modify itself. Of course, a program can modify itself, but with extremely high probability, it won't work anymore. As soon as it randomly modifies a line of code. And how to do such intelligent modifications of programs, we don't know how that works. What we do in machine learning is an extreme simplification of this. We just modify a couple of numeric parameters. All the source code doesn't change. We just modify a few parameters, and that's it. And that's what we understand very well. But this real challenge of self-modifying programs, it never has been solved. Then there was this first theorem prover, the geometry theorem prover by Gelernter, who could prove theorems from mathematical geometry. Then there was this general problem solver, GPS, by Newell and Simon. Of course, it was not general. Then in '63, McCarthy founded the AI lab at Stanford University. And I mean, we still can say today still the AI lab in Stanford is at least one of the best AI labs in the world. Maybe it is the best or the biggest or the lab with the most money. So they At least they have a lot of money, so they can hire the best AI researchers, and they do excellent research. In '65, Robinson invented the resolution calculus, a calculus for first-order predicate logic, and this made the automation of logic really taking off. So based on this resolution calculus, many theorem provers have been built and programmed pretty successfully. Then there was this ELIZA program we already mentioned by Weizenbaum. Oh, and of course I shouldn't forget to mention that Joseph Weizenbaum, who meanwhile he died I guess 2 years ago, he was an AI researcher, but pretty soon he changed into a computer critic. Maybe we should say a society critic, and he criticized, for example, how AI was misused in military, for example, and so on. Then there came this book called Perceptrons from Minsky and Papert in 1969, which was about simple neural networks and their mathematical theory. Then came the European analogon to the programming language Lisp, which is Prolog. Prolog is a logic language, and actually Prolog is much closer to logic than Lisp is. And therefore, for implementing a theorem prover or for doing any logic reasoning, Prolog is a very nice language. I will cover Prolog in the theoretical computer science lecture when we talk about logic, and we also do Prolog exercises. In the same year, there was the first successful expert system developed by a British physician called de Dombasle. He developed an expert system for the diagnosis of acute abdominal pain. So the physician just has to get something like 10 to 20 relevant symptoms of the patient, like where is the pain in the abdomen, does the patient have fever, how is the white blood cell count, and so on, and then input these symptoms into the computer and immediately get a good diagnosis of what disease the patient has. This was a real breakthrough for AI, but unfortunately the whole AI community, which was located mainly in the United States at that time, and de Dombasle was from Great Britain, they didn't mention what de Dombasle did. So nobody knew it. A few years later, these two guys from the United States developed Mycin, an expert system for diagnosis of infectious diseases, which got famous immediately, and in every AI book you can read about Mycin, but nobody knows about de Dombasle's expert system, which was, first of all, it was much earlier, and second, it was much better. But that's what happens from time to time in science. I mean, marketing your scientific results is today, I would say, more important than having really good results. But it's not only in science. In the 1980s, Japan put a lot of money into AI research. It was called the Fifth Generation Project, and their goal was building a powerful Prolog machine. Because at that time, the whole AI and computer science community believed it is just a matter of having good computer hardware. So we need to have this powerful parallel computer, and we will solve all the problems in AI. I mean, I never believed that that will be successful. Even, I mean, I got into AI in 1986. And I got into one of these projects, not funded by Japan, but by Germany. I got into such a parallel AI research project. I earned my money from this project, so more or less I had to speak their language. But I knew, and I told these guys in the project, you will never be successful with parallel computers in AI. Because the complexity of the problems that we have to solve is exponential, or even worse. So a constant factor, suppose we have 1,000 computers, they make the solution of the problems, of course, ideally, in the ideal case, by a factor of 1,000 faster. But what is a factor of 1,000 if we would need a factor of 10 to the power 30? It doesn't help you at all, because you're still left with a factor of 10 to the power 27 that your computer cannot deal with. But that's the type of problems we have in AI. Extremely high computational complexity, and hardware does not help solving these problems. There are so many examples where people can show if my algorithm is a little bit better, that gives me much more than 1,000 parallel computers. For example, in chess computers, there was this computer, Hydra, developed maybe 10, 15 years ago with extreme hardware effort, and at that time it was the best chess computer. A few years later, Deep Fritz was developed, which ran on a little smartphone and was better than Hydra with 1,000, or no, even more than 1,000 parallel processors. So intelligence is not about hardware. It's about software. It's about better algorithms, better principles, and so on. Yeah, this was in '82. The DEC company, Digital Equipment, they built an expert system for configuring computers, which worked very well. And so they say it saved them a lot of money because the machine could do the job that humans did before. Okay, and then in the mid of the 80s, there was a renaissance of neural networks. You see, that was actually 1986. That was the year when I graduated. I studied physics and mathematics, and I guess it was in 1986. We had our physics seminar at the University of Constance, and they had an invited speaker. He came from Sweden. His name was Hertz. He was a neuro scientist, actually a physicist who did research in neural networks, and he presented a talk with the Hopfield networks. You will learn about these too. And this talk was fascinating for me, and that's actually the reason why I'm here now. He showed that there is a little computer program that is able to learn how to recognize written characters. He presented the algorithm, and then after the talk I immediately went to our HP workstation we had at that time and programmed the algorithm, and it worked. It didn't work perfect, but it worked. So, and this was, for me, this was completely new. I had no idea that a computer program could learn its behavior. That fascinated me that much, such that I decided not to continue with physics. I went to Munich, to the Technical University, and just walked through the corridors, knocking at all the doors of the professors and asking them if I could do my PhD there. I mean, most of them were pretty arrogant. They said, what, you as a physicist want to do computer science? You didn't study that. But finally there was this one professor who said, oh, that sounds good, just join my group, and that's why I'm here today. Okay, enough about my personal story. Let's go on with 1990, Pearl, Cheeseman, Whittaker, Spiegelhalter. These are famous names in the area of Bayesian networks. Bayesian networks is the probability theory branch of AI. So they try to solve everyday reasoning problems with probability theory. And this branch is very successful until now. This is really a mainstream of AI, of machine learning, in robotics too. So the probabilistic mathematics, that's what we use today. Multi-agent systems became popular. Then in 1992, the TD Gammon program from Thesaurus was a program that used a neural network and reinforcement learning to play backgammon. And it was excellent. Then in 1993, the RoboCup initiative started, and it still is ongoing. Every year there is the World Championship. And the goal is, in the year 2050, to have a team of humanoid robots that beat the human world champion team. So that's their dedicated goal in the year 2050, to beat the world champion. I mean, I almost believe that the robots, it's almost 40 years from now, and look 40 years back what we had in computer science and what we do have now. So if the development continues like that, then in the year 2050 there will be no chance for the human team. That's what I believe, but we will see. Then statistical learning theory developed, a theory of machine learning, support vector machines. First RoboCup competition in 1997. In 2003, that was the first RoboCup event that I attended. It was in Padua in Italy, and it was really impressive how fast these robots were moving around and how they could control the ball and so on. Now, in the last few years, I would say in 2006, service robotics became a major AI research area. And meanwhile, in the last few years, we have autonomous robots that can learn their behavior. Okay, so that's the AI history up to now. Oh, and we have to stop. Oh. Okay, so let me mention that if somebody wants to buy such a book, you can have it with a discount from me. It's more than 20% cheaper than you get it from Amazon or wherever. Okay, thank you.